everybody. Let's see how this goes today. So what I wanted to play around with today was just implementing interpreters in a little more of a Lispy style than the usual Haskell style, sort of implementing a CEK machine, describing a little bit about what that means, and plugging that together. I moved my camera around here, so I may have to fiddle with this to get the field right. Let's see if we can do this. All right, code. Now I've got the green screen out of alignment, but whatever. The things you have to do. I'm currently trying to get this set up on literally on a pair of milk cartons. That's the tire. Nope, that's the limit. Yeah, sure. I'm going to slide it back a little bit so I don't hit it with my chair. Even if I don't get perfect framing. Maybe I can lower that a little. Something. Alright, that looks more or less it. I'll just duck. I guess that begs the question of what is a CEK machine, how do you implement one, etc. I kind of want to play around with a trick from Paul Chiasano on how to get sort of free compilers from interpreters on the JVM. And so that's going to be my end focus. But for that, first we need a basic machine to even see what the heck this could look like. All right, so let's build a little CEK machine, I guess. And I apologize, I don't usually do these, so I might get this totally wrong. So I could actually use some help from the audience as I go, possibly. Module, let's build a CEK machine. Oh yeah, Matt Might is kind of the king of this space. So we'll try and do a CEK machine, maybe upgrade it to a CESK machine. We might talk a little bit about the whole abstract interpreter stuff that Matt Might is the god of. But we're going to hopefully stick to something pretty simple. So what do we want our programs to look like? So a CEK machine, like it's C for code or context, or I don't remember. E for environment, and K for continuation. And then eventually, when we want to do some stateful stuff, we'll start bolting in a store. Control. Matt is far more the authority on this stuff than I am. So our control component is going to look like, let's just build an expression type, and we'll fiddle around with this. We have a variable. We have a lambda, which is like given a string. We have another expression, and maybe we have app. I'll just do an untyped lambda calculus, mainly because that's making it interesting, goes beyond the scope of what I want to do today, I think. And our environments will just be functions, I guess, from looking up variables. There's no real point. We'll just make this a type synonym. And then continuations are going to be the different contexts in which we can execute. This is going to basically be our stack for right now because we don't have call CC or any of the schemey kind of bits. So our continuation would look like, are we at the top level? and then we'll add a couple of more bits and pieces to that as we go. And like, so a CEK machine is typically implemented as it would be implemented as a small step semantics. Whereas we could also talk about this in terms of like big step semantics. So a small step semantics would say we have some kind of state, which is what is our control, what is our environment, and what is our current continuation. Why is it spelled with a K? Because CE is taken. And for various reasons, they like to use Ks for continuations. But mostly because C is taken. By code. So we have a state, and basically what we're going to do is we have some kind of step function that takes a state to a state. And this would be typical of a small step semantics. And then we have some kind of check to see whether or not we're in a final state. And then we iterate our step function until we're in a final state and we accept it. There, we even have a function for this. Somebody mentioned it to me recently. In the prelude, there's this function until. So basically, we're interested in running, it's basically until we're in the final state, step. Which will take a state to a state. So again, until looks like this, and it's in the prelude. It's a very little use function. I guess we would call this like eval or evaluate. So what we need to know is basically whether or not we're in, what do we have? There was a comment from Alec just now. Q&A. Or maybe, I don't know where it came from. Q&A, loading. We're not getting the Discord chat. Come on, Discord. What the heck's going on? Maybe I have to run it on the other machine. Hold on a second here. Let's see if this works. No worries. I just want to actually have the chat going. Pop over there. So I'm not getting the Discord messages on the chat for some reason. Partially because I had reconnect over here, damn it. So I'll just hide the Discord overlay. Twitch. Somewhere in here is the rest of that bit. I have a little Haskell logo stuck on my face. That's just me fiddling around with this thing. Viewer count, that's fine. Alert box head, colored light. No, that's fine. That's fine. Logo. There it is. Aha. All right, I've at least removed the Discord chat from the screen. So going back to the coding view, I can at least see what's going on. SECD is use C for control string. And the CEK machine was invented by a German. Okay. So basically what we're going to be doing is sticking our program into a state by starting with some starting environment and some starting continuation, stepping it over and over again until we're in a final state, and then accepting it. This would be the small step approach. The big step semantics approach would be that we use a recursive step function that just keeps running until we're done. There's some benefits to each. The small step semantics approach has the benefit that we can stop the whole machine, inspect the stack between any individual step, etc. We could get that by taking a big step semantics and like running it in a monad and then putting hooks in the monad for where we want it. So it's not they're not irreversible. They're not completely unsurmountable differences between the two. It's kind of easier to do garbage collection on small step semantics, etc. I'm not necessarily sure if I'm going to be able to get away with a small step semantics for my final goal here. So we're going to implement a small step semantics and then tweak it to build a big step semantics. At least that's my plan. Insofar as I have any plan today. All right, so let's see if we can figure out how to do eval. Or not eval, step. So step CEK. Oh no, it's going to be a state CEK in the current form. We're going to need to basically case off of whatever C is. If it's a reference, we're going to do a lookup in the environment. Oh no, our environments are going to be, we're not going to be getting expressions out. We're going to have to get a whole value of some sort. And a value would look like closures. Closures would have some kind of expression that we want to run and an environment for right now. We'll see if we can go through afterwards and make this a little less stringly typed. I wanna maybe get this like expression of A, and then have this lam take a maybe A or something more appropriate, and then our environments will take type variables and whatnot. We're not there yet. I want to get a basic kind of map-mite style version of this. I'll have to follow up on Bolu's link after. So basically what we're going to do here is do the lookup in the environment. So we've got a variable. We have an environment we can look up the variable in. And the only thing that it could possibly be right now is a closure. This is a closure for some variable, some expression, and some environment. And what we're going to do here is just give back the modified state that we want. We're looking for a lambda for this variable with this body, and we've got our modified environment and still have the current continuation. So we're looking up the, I think I've got this right. We're looking up the closure in our environment. We get one out. There's nothing else it could possibly be. And we're done with ref. Applications. So here we have, like, here we're going to actually have to do something a little bit messy because we're going to need to know, we're going to need to kind of push the step, like we're going to, CEK is going to try and go in and evaluate the argument first, typically because this would be for a call by value language. So we're going to compute the argument and then we're going to have to pop back out and then go in and do the, compute the function. Did I say ref? I meant var. And maybe we can maybe we can try to do the Coda Brown thing. I'm not quite equipped to do it today. I actually do think that there was a paper recently that that Codalio is referencing here, where Connor McBride wrote a article on, where is this? It's very recent. Code Brown indices, be 2018. He can probably pull up the. Nope, that's not it. That's Gergardi. Dolio, do you have a link to that? That way I'm not sitting here trying to find it. Oh, Bolo linked it. Great. All right, yeah, everybody's got to be somewhere. So this is so if you look at de Bruijn indices, they're like, it deletes them from the environment, it deletes unused variables kind of at the last possible second. My bound library, which is the implementation of the Burden-Patterson thing referenced halfway through here, deletes it somewhere in the middle. And this says that it gets rid of them as soon as possible. Everybody's got to be somewhere. That's the pithy little Connorism that goes with this one. All right. So we're not going to get there today. At least as I understand the world. All right, let's see if we can do this. So applications. We're going to need to basically say, hey, look, I'm not at the top. I'm working on an argument. I have an expression in an environment and a continuation to come back to. And what are we going to do here? We're going to say we're moving into a state where we are just looking at, what are we doing here? Did I move into the, I want to, let's see if we get it wrong. State F with our current environment. I should maybe name these something. C prime, C double prime, I don't know. CF, CX. Now that I know that they're control. State 4, we're going to step into CF. We'll see if we're lazy or if we're called by name or called by value after I get this thing done. We've got our application. We've got an environment, which we didn't touch. And I need a arg continuation for CX with our current environment and our current continuation. So I guess we're going to step into the function first. Yeah, this is about as extreme as I go, variable name wise. I've used 2 letters. And now here we've got a lambda for some variable and some body. And we're going to need to do different things depending on our context. So this is basically how do we step. If we're trying to evaluate a variable, we go look up that variable in the environment, grab its closure, and then step into it. If we are looking at an application, we step down into the function side. If we're looking at a lambda, we need to distinguish based on the current continuation. And if we're at the top level, we're just done. We don't go anywhere. We're stuck. And what are we stuck with? We're stuck with this and our current environment and continuation, which is top, obviously. There. We just don't change. So final here will be basically, we're in a final state if we're in a state that is looking for a lam. Anything top. And nothing else is final. So King of the Homeless, the bit you missed at the beginning was basically what I said we're going to do is we're going to implement a small step and a big step semantics for a untyped lambda calculus using something called a CEK machine. And I have an end goal here that I don't know if we're going to make it to. I'm hopeful that it'll work. I want to try and I'll try and tie this to a talk from Paul Chiasano about the way that he implements the performance, the runtime of Unison. And so this might, if we can get this to work, maybe we'll install Ada and see if I can try and figure out how to do this for CEK machines. var is not final because you can if you have a var, you're able to look it up in the environment and get a closure and continue stepping. If that variable was free and we had some notion of, hey, a free variable that is missing from the environment, then maybe we could have another kind of final thing. But in the event, we're looking at an arg, and we have CX here, and some modified environment and some modified continuation that we want to carry on with. We're going to move into a new state with that thing, our modified environment, and now we're going to have to do the other side. So we need a new continuation. We've got the function. We've got the variable. We've got the body. I've got the current environment and the continuation. So I'm going to need to make some kind of continuation up here that does, you give me a variable and a body, which we in our current setup here is just an expression, and an environment and a continuation, I think. And all this stuff should be banged to heck. So we will make Johan happy and use the strict data extension because nothing here needs to be lazy in its data. Fun BBEK, I think so. And we made it fun. So we've got fun with this variable, with this body, with this environment, and this continuation. I think that's right. Let's see here. And then the only other case is that we're in the fun context. So we've got a variable y, I guess, with some body. I guess we'll call this v prime and b prime. This is going to get messy. And some modified environment and some modified continuation, and we need to give back a state. we're here. What are we doing? We're going into state will be the body. We have to do something to our environment and keep our current continuation. So here what we're going to do is what? We need to extend our environment with the new variable. So we're going to extend our environment E with v prime. And we're going to set that to, we need to build a closure for it. So it's going to be a closure that holds on to, well, for this variable and binding, this is really messy. Hopefully I've managed to pull all of these things together out of my butt all the right way. Closure for this variable and binding and the current environment. Yes, closure needs three things. So we're extending with this variable, this thing, our n prime. We just need to figure out what extend means. Extend says if you gave me a variable and a value, I will extend an environment and give you a new environment. So here it's, I've got a variable that I'm looking for. I've got a value. Just call this KV. I've got an environment, and we are building an environment which is just a function from string to value. So I've got a, I guess, for this I, I'll give you this value. I've got a j. If I is j, then we're going to give back v. Otherwise, we're going to give back whatever f was going to give you. Annotating the fields of my records. Which ones? These arg things? Maybe we could let me see if I can finish the thread of reasoning that I have, and then we'll come back and do variables. We'll maybe undo the variable soup. I don't want to try and switch my mental mappings midstream. I think I've got everything done though. So we should be able to find like a starting state, which should take a expression and give me a state. So start with some piece of control. And one of the reasons why I was trying very consistently to pick like CE and K and try and respect that was because otherwise it does become value soup. So start with a given expression gives me a state with this C. The environment is empty. And the continuation is going to be we're at the top. And so let's maybe build a little function. The identity function would be a lambda x with a body var x. And we should be able to build constant function is like lambda x, lambda y, with a body var x. This will be a little better. Does this actually work? Maybe. Wow, it actually compiled the first time. So if we start with the identity function and we step it, oh, we need to start the identity function. I didn't build a show for state. And here's the problem that our environments don't know how to show, so we're going to need to write a manual instance of show for state for right now, I guess. Shows prec state CEK is what is this? This is like we'll just kind of shows prec 11k. Ah, crap. We've got these, you know, these environments getting really annoying. New type environment. And then I don't have to do this thing. I can just derive it. And then I can just driving show. I can switch to a map. We'll see whether we want to stay with anything functional here later on. These will probably become just like lists and we'll index into them or something by the time we're done. So I'm not really too wedded to getting this to like have a pretty version of environments. I care about the environment functioning. So here the extend thing now takes an environment to an environment. So this is going to be an environment, and this is going to be get env. I guess I can just call this like bang. That'll be getting fancy. I guess I can use multi-way if. Or I could, I'll just do it with the, because there's no point, it's not really multi-way. There, so we've extended our environment. I'm gonna have to rewrite all the env stuff, yes, because I made the use of the environment into a bang. So this was the only thing that looked up in the environment so far. And yeah, multi-way if would have made that a little less minimal, or a little more minimal of a refactor. And we've had to rewrite extend. Constant defined is no longer there. I have to make an environment that is constant defined. There we go. Start id, applied to id. So we start here. We step it again. And it has reduced itself one step. Step. What? Look that up in the environment. We're stuck. All right, so we've managed to write a small step semantics that is walking through our, and yeah, I usually just do lambda case. The problem here is that our state is buried in our CEK and blah, 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 blah. All right, so we've at least managed to build an interpreter, which I'm actually really impressed worked the first time. I'm going to copy this. Off to one side, because I don't want to lose it. Now maybe we could, I actually don't know how well this is going to work. Let's try and make this a little less stringly typed. So I have a, and here what I've got is an expression of maybe a, and I've got an expression of a and an expression of a. Let's see if we can do that. Yeah, I'm using unary to brown sort of by hand. This has the benefit that now expressions actually become a monad and we can do all sorts of things. And environment is instance. And now, this is an expression that wants a, this is an expression of maybe a. And we have an environment for a, but I don't know what a is. A exists, so I have to, let's just rewrite this into the other style. Closure. You give me an expression of maybe a and an environment of a. I'll give you a value. And cont now looks like this. Top is a continuation. Arg says if you give me an expression of a and an environment for a, I will give you a continuation. Actually don't know if this all will work. It seems like it'll work. Expression of maybe a and an environment for a, I'll give you a continuation. And now my goal is to have my state be state will take an expression of a environment for a, and a continuation. I'm hoping that this will all work. If I go to look something up in the continuation, I'm worried that I'll screw up somehow, but we'll see. Oh, this is and a continuation. I'll give you state. I might not be able to derive show for these things because they're in this form with existentials buried in them. Where did I screw up state? Or is that from a comment from before? Or arg took a cont to account. You're right. There's a continuation buried in the argument. This is the same mistake I wrote down state. So I want like a expression of void. And I'm going to need, yeah, GADTs and stuff. So here is a function from void to anything. So this is just, we'll start with absurd. And we'll start with the top continuation. And I need a proof that these things are closed. I need a little smart constructor for lamb. So let's make lamb take a literal lambda or something. Lamb takes a and an expression of a and gives me an expression of maybe, just an expression of a actually. As long as I can compare these for quality, that'll be good. I mean, I can further unsettle folks. I mean, that looks a little more legible. So lambda a body is going to be something like skim through this thing. Let's make a little abstract function that takes an a and an expression of a and gives me an expression of maybe a. Lamb a body is abstract a in the body, and then wrap that in the lamb constructor. An abstraction is going to be take an a and a functor f here. This is going to work for any f. And what do? We're going to fmap something over f here. Or what do we do if we see another thing such that a equals b? We're going to give you back nothing. And then otherwise, there's a nice way to do this with lenses, but I'm not going to bother. Where's the eta contraction bit? Manip. So abstract AF go, oh, this one, got it. Sorry, Ruben. I'll see about playing with the quality settings in future streams. I don't really know the right level to do this. I think if I hit partner, I get some like live cross encoding options. But I'll see about lowering it maybe 20%, like 30% or something like that at least. But as for hitting partner, I only have 49 viewers right now. I think I have to average 75. So we would need to grow the number of Haskell users watching me by about a factor of 2. And I'm also looking to do a fair bit more streaming, I think, in the future. Over the course of the next couple months, I might actually start streaming during the weekdays a little bit as well, which will help get the number of streams up to make it possible to do the partner thing. I don't know. I'm still learning my way around this whole Twitch business. So what do we have? We have lamb. We built it on abstraction. What else do we need? So now I can actually write these more or less the way I had. Lamb. And the only difference is I need this closed combinator And closed is going to be something like, given an expression of A, I'll give you maybe an expression of anything. And closed is going to be like traverse const nothing. Go make sure that there's nothing left in it. Yeah, so we're going to walk through this thing, and if we see any variables left, then we fail. Otherwise, it will succeed. So we made a way to build a closed term. And we could do this as expression of void to maybe state or something like, or expression of A to maybe state by bolting that in here. But I think starting from an expression of void and then requiring these id to be a closed term. Would be good. Yeah, I can lower the FPS to half of this. So we have an expression of void, we have state, we have values, continuations. What do we need? Step. I mean, hopefully that would just magically work. So here, what are we doing? We're saying I don't actually need the string here anymore. I just need the value. I'm going to take an environment of A and give you an environment for maybe A. So what are we doing here? We're just basically giving you the nothing case. So this is extend. What are you doing? What's your default? This is maybe value F. That's kind of cute. Yeah, I did. I raised the bit rate really high because I wanted to have high quality, and then it because I was getting really bad blocky artifacts the first time I tried streaming, and then I didn't bring it back down once I realized I didn't need the throughput. Yeah, I can't do it now. We've got extend, we've got final, and eval is still in the right form. The original definition took what was the variable that we're using, and now we're going to be doing it on the nothing. So we haven't fixed any of this stuff up. We haven't looked to see, because closure now holds on to a particular variable or something like that. So here we have a var v. We're looking it up in the environment, which I think is okay. This should have been a v prime anyways. We should go back to the CEK simple. Yeah, Shikado. So what we're doing right now is building an interpreter for an untyped lambda calculus using a technique called a CEK machine, which is a kind of traditional virtual machine for implementing functional languages. All right, so what do we have? We have a CEK abstraction lambda. We have this ability to build closed terms. We're starting to make this thing strongly typed. I almost believe it. Here we've done the the lookup, but now closures don't carry a variable. This body is just a exp maybe, so that's fine. We just pass it along to there. The environment prime from our closure, hopefully, is of the right form. Yeah, the closure had an expression of maybe A, and this had an environment of A, but when I put the B into the lambda, I get an expression of A, and I think we're good. And we need, yeah, traversable and all that stuff for EXP. If I really wanted to dog food all my own stuff, I'd probably build this off a bound or something. I'm not really going to right now because, yeah. First step is let's get this all rewired. So we've got the closure simplified. We've got our state, lambda body, state arg. Arg is still okay. Lam doesn't take a variable anymore. And so for top, we're done. We have an arg. This didn't take a variable anymore. And fun no longer takes a variable because this is implied. We're extending that thing. And this didn't take a variable either. I think we might have got that. There's no way this is going to decompile. Now this is in base, this is a lot easier. I guess, where am I? I'm in CEK. What's the ghcid command thing for just taking a individual? ghcid ck.hs, will that just work? Yes, there it is. Can't do it because of existentials. That is true. What do we have here? Arg and fun. Because I'm lazy. We'll just bake enough information to show it. But then I'm going to have to build manual show instances for const and stuff anyways. Arg CEK is show paren d is greater than 10. This is tedious. Body K. Okay, I think that's right. I would have hoped, unfortunately, driving isn't that smart. Here we have the same problem. have that. What are we missing? 65. EXP void. I'll just assert. Functor exp. We'll derive traversable for this thing. Functor foldable. Traversable is just as in data maybe. That is just from just. Show a one from use of state. Where are we there? We got a var v. State knows why did that blow up here? Show A1 for closure. Does closure not know it's able to show? All right. Plausible, 81. A1 is rigid variable bound with a pattern constructor fun and state. Which one's the case that's blowing me up? Is it this one? All right. So everything else seems to be happy with me. Did we screw up that? Or that? There. So that actually probably indicates we had a bug in the original. Looks like we screwed that up. So we had a bug. So making more complicated types. Found a problem, but this actually worked, which amazes me. Let's see what happens if we go to do the exact same thing we did the first time. We'll start with app. We'll run it. We have a lambda with variable 0 in it. That's de Brown. So let's just start with the original version. Here we're applying the, let's see if I can get the mouse over to the right window. The identity function to the identity function. At the very start, we step it one time. We now have, we're in the context where we're evaluating the left-hand side of this. We have a lambda. We step into that. We're now stepping out into the fun state. We step into that. Now we're looking at variable 0 in our environment. We still don't have any good way to describe our environment yet. We'll go back and maybe make that less of a function and more of a map or something like that so we can see it. We look the thing up inside the environment. It's just the identity function. And now we're at the top and we're not going to terminate. So we should just be able to do, hey, eval this thing. And it runs until it hits that final state. Yeah, other than that problem. But it should have started off doing nice things. Yeah, the first couple steps. All right. I'm actually really happy that that actually worked. Let's flesh out the rest of this stuff, just the kind of boilerplate. We really want to, I want a monad for expression. I'm only working on GHC 8.4, so it doesn't really matter. I don't need the return. I'm going to need it later. Bind. Var A bind to F is just F of A. That's a monad law. That's return A bind to anything is F of that. App of left and right bind to F is app of left bind to F, right bind to F. And the only interesting case is lambda of a somebody bound to F. And there, what do we have to do? Well, let's figure it out. It's lambda of something. We need an expression of maybe B. We have F goes from A to expression of B. We can see it over here on the right-hand side in GHCID. We have B is an expression of maybe A. Using deriving via, you can get the derive applicative thing. I think that's 8.6 that driving via went into. I haven't actually really been paying too much attention to it. Let's make this underscore F prime. There we go. Maybe A to expression of maybe B. So let's just lambda case. If it's a nothing, we're just going to pass out a var nothing. If it's a just A, we're going to call F on A, but F of A is, I need to take an expression of B and turn it into an expression of maybe B. So we'll just F map something over that, and that something will be just. So now we've done all the de Bruijn index manipulation stuff. This is everything that the bound library, one of the things that the bound library deals with for you, in exchange for you having to write all those annoying eq1 or 1, etc. instances, which are a mess. All right, so we have a monad for expressions. We have traversable for expressions. We have a way to check to see whether or not an expression is closed. We can build lambdas. We've built typed environments, which I'm pretty happy with. What else do we need? So we're starting to get a sense that we could replace our environments with just like a integer of bound variables or something, and then some mapping for free variables for context that we could go look stuff up in, some meta context. What do we have? Applicative monad, abstract closed, ability to show our continuations. So we were all right, let's take a quick couple-minute break. I'm out of Diet Coke and want to keep my throat wet. I will be right back, and we'll figure out our next steps. Probably doing a very simple big step interpreter just by like inlining some, like getting rid of this eval as a special thing. All right, we're back. And I have sufficient caffeine to keep going for another half an hour or so. We'll see how this goes. So right now we've got eval implemented directly in terms of our small step semantics, but we could do a big step, which is to take our state all the way to the final state. So one of the things that kind of annoys me about our step function is that it has to have this this sort of like handle the top case and come back to where you are. Let's do a thing where instead our step function just takes a state to a state, and instead of calling state with these things, let's make it just take the expression of A, an environment of A, and a continuation, and give you the final state. Big will take C, E, and K. And instead of calling state down here, we're just going to step, 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 step. Now, I screwed that up somewhere. Step takes 3 arguments. I kept calling step. All right. Now, usually what you would do is you wouldn't use an explicit stack for your big steps semantics where we have like Kant acting like our sort of machine stack. You would borrow your host language stack. We could probably transition this to do that. But sort of why am I trying to do this? So let's see if I can get to the sort of punchline. So there was a nice little talk given by Paul Chisano at Scala World last year. On how the behavior of unison works. And this is the thing that I want to exploit. I will give you the link. Meanwhile, I'm going to kill the audio from it. But the clever bit of this talk, I mean, this is a great introduction to the idea of what it is that I want to do, is that he builds a interpreter in a fairly direct fashion and then exploits the JIT to turn around and turn it into a compiler using something called a Futamura projection. So the idea of a Futamura projection is that what we want to do is take our program and specialize an interpreter for, like, the first degree of it is like specializing an interpreter for a given source code, you get an executable. Specializing an interpreter, specializing the specializer gets a compiler, etc. And so this is the sort of the idea behind PyPy and behind Graal on the JVM, etc. And he applies it to sort of a fairly simple machine where he's got like integer operations as expressions and like can do blocks of integer operations. And starts with a very simple interpreting function, which is doing a lot of work analyzing the expression that it wants to interpret. And then it's doing some work that is manipulating the environment or the that is actual real work. So this is all the stuff he's colored in red versus green. All the red work here is busy work. It's figure out what to do next. It's the kind of thing that says interpreting this is not actually beneficial to running my program. It's the kind of thing that, well, maybe I could switch that to a bytecode, or I could switch it to a more efficient thing, or I could write a custom thing that spits out Java bytecode for this. But we have this wonderful thing for us on the JVM. We have a JIT. And so if we were able to separate the decoding of the expression from the stuff that's running on the right-hand side, then what we could do is get the JIT to, like, get this thing to spit out the program that we have that we want to run, in this case on arrays, in our case on our E and K component, on our stack and our environment and continuations. So the manipulations of our environment and continuation is real work, and the reading of the next instruction to do is not real work in some sort of deep fundamental way. So what I want to do is curry this, which is all he does. And so he's building a compiler from expressions to functions, and then saying, hey, JIT, please JIT my function. Like, that's going to run out of the box today, after you've run the function for long enough. And he finds that he can get generally within about 50% performance for these kind of simple array computations. The question that I have, and I do not actually have the answer to this is me coming into this stream pretty cold on this, is whether we can get away with this on the JVM today. If I could turn around and run this code or something like this code on the JVM, could I get a CEK machine to turn into a compiler by using a JIT? By using the JIT to execute the second, like the later stages of Futamura's projections for me, so that I could get a efficient CEK machine out of running Haskell-like code on the JVM. But fortunately, we have a way to run Haskell-like code on the JVM. We have Ada. So a couple of years ago, Rahul Matnini, for those of you who are not familiar with Ada, worked on a project he called GHC-VM, which was a port of Haskell to the JVM by compiling down from the back end of GHC into Java bytecode. And after the summer was finished, he continued working on it and spun up a company called TypeLead, and they joined Techstars through a tech incubator thing, and they have been trying to build this lovely language that has all sorts of polish for running Haskell in the JVM. So the idea here is that instead of compiling in the usual sense, what I want to do is have the compiler spit out a lambda, or have the step function turn into a lambda that when run over and over again, the JIT will eventually fire and turn that lambda into the straight line code you would have tried to compile in the first place. That's what Paul's idea is that you just run this thing and let the JIT figure it out. And then later on, there's some thoughts that because of like the existence of Graal, that like the JVM compiler interface has given us more machinery to just ask the JIT to do things. So maybe we could just ask it to compile it now because we know we want it to compile. We've done the boring step. So maybe we can instrument this a little bit more and get closer to the 1x that Paul was chasing. And yes, the JVM will devirtualize those internal calls to intermediate lambdas because they're all to concrete things. So they'll become monomorphic call sites, which then just inline straight through. As for how well it'll work in .NET, that's a whole other can of worms. So I'm kind of interested in this as a potential like short-term execution strategy for Coda. And so I want to explore whether or not I could use this as a way to avoid having to write a full-fledged compiler for this ridiculously complicated language that I'm working on. And so this is the end goal of this like stream today, is to see like kind of the general direction that I'd have to go to manipulate the CEK machine to see like how much of this really could be curried out. Like given just the C, can we get the EK parts to get to the final program? And I think in order to get there, I think it's kind of apparent to me at least that I'm going to need to move from the small step semantics to a big step semantics, where this is the recursive call. And I'm going to still need to keep the explicit stack for my continuation in order to work with it. But I wanted to, first get us introduced to CEK machines, because they're going to be useful later on if I want to talk more about abstract interpretation, and the work on, like, abstract interpretation. The work on supercompiling also needs some kind of CEK machine in order to do it robustly. But we're going to need to manipulate this a little bit further. We'll need to get to like a CESK machine to actually fully be able to do abstract interpretation and the like. But yeah, so my goal is get a general frame, like a kind of the idea of how we would do abstract interpretation, get to the ability to do these CEK. Why does supercompilation need a CEK machine? So there were... doesn't need CEK per se. It needs an abstract machine. So there was and you would need the S in the CEK machine. There were two talks on supercompilation at ICFP. One was Neil Mitchell, and then who was the other talk? This was a few years back. Was this the Ulmer talk? No. I'm trying to remember the other talk on supercompilation at ICFP. Supercompilation machine, ICFP. Here's where I'm sitting here just randomly Googling words to try and find the thing. I was not actually prepared to answer that question. I'm actually really embarrassed that I can't remember who the other person who gave the talk was. So there was the original Rethinking Super Compilation post by Neil Mitchell, and he kind of came up with an ad hoc mechanism. And then later on, he gave another talk on doing it with a slightly less ad hoc mechanism. But there was the same year, super compilation at ICFP. Who was the other guy? It really is embarrassing to me that I can't remember who gave the other talk. Come on. Super compilation ideas and methods. No, that's not it. Is it Max Bolingbroke? No, that's super compilation by evaluation. So the idea was that if you're trying to do super compilation and get it to actually iterate out into some kind of termination condition, the set of all of the contexts in which you want to do this, they modified like I think a sesstuff machine or something like that. Maybe I can find it through that. I'm doing this off screen because that way all my embarrassing search terms don't show up on the... Let's see here. Super compilation by evaluation. This looks right. This is okay. It's Max Bolingbroke and SBJ. So they build up their termination criteria by building a more. I think they use a sesstuff machine. Anyways, I will just dump the link to the paper in chat, and then folks who have more bandwidth than I do right now can look it up later. Yeah, 2016. This is the right year, because I think that was the year that, or 2016 or 2015 was the year that Neil Mitchell and I think Max or somebody gave talks kind of back to back on super compilation. All right. So what I want to do, I think, before we get too much further down this, is I want to convert this to a CEK machine. So we have some idea what the S in a CEK machine would be. And I want to get a general idea of what abstract interpretation would look like. And... I think I still need to keep this thing running with an explicit, like cont for our own stack. We have to build the explicit stack, even though we move to a big step semantics, because we can't really rely on our host language's evaluation model if we're going to start doing, if we're going to JIT everything I want. Maybe we can. The concern that I have is, like, on the JVM, I don't have tail call elimination, and so that becomes a damn mess. So maybe what this is you call a thing, and then this hands back out something, and you have to trampoline it, and then you have to hope that the JIT will work. I have had horrible results getting trampolines to work with JITs. All right, so how do we tweak this to make a CESK? CEK typed. Maybe I should have done this before I bolted all the crazy types and everything. So the idea here is what we're going to do is we're going to add a store. And stores hold values. And what we're going to do is the continuations will be values placed in the store. And the idea is right now, continuations hold direct references to the next continuation. One of the values of the CEK machine is that nothing holds direct references to other things. They always go through looking up in the environment or the store. And by doing so, now you can start doing things like approximating these things with like simpler like approximation domains. Like they're integers, and it could be positive or negative or 0. Let's say that that's the abstract domain we're going to work with, and then we do abstract interpretation using those things. And then the store could be an approximated function from a smaller set of cells to values that are sets of possible values that could be in the cell. And you can do abstract interpretation that way. And so this becomes useful for things like control flow analysis, etc. It's one of the reasons why, like, Milton is like CPS is because it enables like all of this control flow analysis, etc. kind of stuff that Matt Might loves to talk about, or used to spend a lot more time on talking about. Is because like by getting rid of the specialness of the return continuation, it's really easy to talk about context. So how would we do this change to our store? We're going to need what? Our values need to get smarter. So we have closures, and I guess we have a continuation. So cont will be some kind of, will just be another variable that we're going to look up in our store. We first need to, I guess, define the store. Shit. Here's where I'm actually starting to fall apart here, trying to figure this out, because I put all these types in. And I don't really know the way to do this off the top of my head. All right, let's see if we can steal from Matt. Matt might writes lots of lovely articles on this stuff. CSK machines. So he builds all this stuff up in Scheme. His store looks pretty simple. Let's see. Expression, environment, store, and continuation. The store is going to be from address to value. Oh, and his environments are now looking up addresses. That's interesting. And he's got a few value types they can shove into his into his store at different addresses. And what's his cont type look like? They're either these let continuations for let bindings, or we're done. This might actually be a bigger chunk to bite off than I want to do right now. I might need to take a break, figure out how to do this, and then do this in a subsequent stream. But at least we have the mission. So I do want to put together a little bit of a straw poll about what folks think about streaming during the week. What days work best for folks. What's a good scheduling poll site or something like that? Doodle, that's the one. So I'd like to pop in here and figure out days of the week that work for folks. What are the options? I don't actually want to do things too early. Should run longer, actually. Like up until now, I've been just running on the Sunday. And these run at least a couple hours, let's be honest. I will definitely be diving into type checking in subsequent streams, I think. I'm not really equipped to do it today. Let's see here. So I think those are probably the best general windows. I'm going to use the particular days of the, like the actual dates here don't matter. I'm just trying to get the days of the week. Let's go back here and maybe put some extra time options in as well. Add more times. Oh, great. I can just do it maybe in bulk. 5 p.m. to like 7 p.m. my time. And I'm not getting up any earlier than that, so nothing else is really going to happen. Sure. Indicate if a time option is not ideal for them. Don't really care for super detailed responses. Any help with reading Heisenberg's thesis? No, that's a mess. I mean, it's a beautiful thesis, and it solves a very, very hard problem, but it's a really complicated approach because it has to integrate with all the other things that GHC does. Sure, continue. Maybe I can get a I am me. Great. Can I finally put the poll up, please? Invite participants with this thing. Testing the poll. Live coding with Haskell. Pick a date. Pick a time. In theory, that should give options for people to poll. Did I get that right? Okay. There's a poll for folks to say what times or what time of day and what days a week work for them. I'd like to just get some feedback. I'm going to try and I think I'm going to start trying to do a few more smaller streams rather than just go and go and go and go and go for 4 hours. Because while I enjoy that, I know it's exhausting to folks. And I am willing to do any of those, so that's fine for me. But if there's a particularly large lump around some of these dates, I will, or some of these times, the dates themselves don't really matter on this poll so far. All right. So D-Split says for why Haskell, I mean, that's a big question. I write in Haskell because I find that when I work in Haskell, people can build on top of my code and it scales. That's not a particularly deep insight. It's but like for more general reasoning, I think Haskell is the only language that takes laziness seriously. And I think laziness is a thing that you need to start considering once you've embraced immutable data structures. Mainly because if you start saying that I'm going to work with almost all of my data structures in my world immutably, then if you're naive about that, you can actually prove that in a strict language that doesn't have any mutation, that this will cost you a log factor for some things. But that in a world of laziness, like once, if you read Chris Okasaki's book on purely functional data structures, he goes through and spends most of the book using laziness to fix that performance gap. And so to me, laziness is almost a natural consequence of wanting immutability, and immutability is something that I generally want because it makes concurrency and parallelism and all those kind of things better. I mean, other people use Haskell because it's easier to reason about and whatnot. But those are my reasons. We're starting to get some actual responses here, fleshing this out. I realize that there's a bit of implicit bias in the sense that folks are already here on the stream right now, so this has to be a slightly better time for some folks than others. So I probably won't have the result of this poll on the stream here today. So D-splits, I think one of the things is this: when you pick up most other languages, you're just learning a little bit of syntax. You're like what's the syntax for an if? What's a syntax for this? What's the syntax for that? I think Haskell has a reputation for being hard to learn because it's the first language that most people encounter where it's not just a little bit of extra syntax, where the ideas are actually quite a bit different, and because they're trying to deal with laziness correctly. And so in most languages that you've touched, like if you ever touch an integer or something like that, then that integer is actually a machine integer or something like that. In Haskell, it's going to be a promise to compute an integer when you actually finally look at it, and when it finally does, it's going to replace itself with the answer. And so if things don't happen until you finally look at them, like until demand, you can prove that then more programs will actually terminate under that evaluation strategy than the other. But that has knock-on consequences the way you think, right? Like printf debugging becomes complicated when you don't really know when something is going to be finally forced to evaluate. You can't just have things launch missiles the moment you look at them. So the Haskell community had to get very good at handling side effects explicitly. And in some ways that turned out to be a huge win for reasons they didn't really anticipate. Like just being able to do concurrency and whatnot in a Haskell program is really, really easy. Like it's an afternoon kind of thought. Whereas in most C++ style programs or whatever, it's a PhD thesis to add significant concurrency to an existing program unless it's very well engineered. And so the fact that they had to figure out all this rigor around monads and all this kind of stuff just to deal with printing to the screen and launching missiles made Haskell required a pretty deep well of ideas. And so a lot of learning Haskell is learning this pile of abstractions that apply elsewhere, but weren't necessarily spotted in the wild in those other places. Is Haskell culture detrimental to just normal business feature development? I don't know. In some ways, I find a lot of people who are just building CRUD apps are the folks who have embraced all the lens kind of stuff more than the traditional Haskell core. Even though the lens stuff is built on all the crazy abstractions. and it's mostly just because it allows you to do things like like drill into your state, into maps, into JSON documents that you have coming from somewhere. And yes, I mean, the people who write publicly about Haskell being hard are the people who don't do Haskell, and I mean, they're the people who bounced off. There's a selection bias, I freely admit. All right, I think we've derailed pretty far. I'm going to take this poll. I'm going to drop it on my Twitter feed to get a little broader feedback from folks. And I will take this generally in mind for scheduling subsequent things during the week. And I think next time we'll pick up with maybe trying to do the CESK thing, or maybe I'll have Ada installed and we can try and play around with getting a unison style interpreter / Futamura projection solution. Because I would really like to be able to just write a CEK or CESK machine, write the denotational semantics, or write the semantics of the program that I want to write, and just have it turn into a passable compiler. That would remove a lot of fear from me for the development on a current project. And I'll if nothing else, I'll post this as a gist or something like that, and I'll link to it from the Twitter feed. So the Twitter feed is linked below, or my Twitter feed is linked below here, and I'll post it there. All right, I think that's everything I have. So I will bid thee adieu.
You're still here? It's over. Go home. Go.